Hi, now we're going to go through this paper as paper one. First one is looking at the subatomic particles and state the difference between the three isotopes. So we're looking at the subatomic particles. So we need to talk about the particles here. It's not about just mass number, it's really about state number of protons, same number of protons, but different number of neutrons. So it's looking at the actual particles. Okay. Next one, state how all of the chemical properties of these isotopes differ. They should all be the same. Why is that? It's because they have the same electron or electronic configuration, or same number of outer electrons or something along those sort of lines. But it's looking at the arrangement of electrons. Right, this is based on a relative mass calculation. Now, you should be able to set up a calculation where you've got the relative mass and you're looking at the isotopes and their abundances, but it's turned it into a bit of a maths problem because it hasn't given you all the information. This question appears infrequently, but it's irregular. So what we need to do here is work out what we have, and we've got isotope 25, and we've got 10% of that. Isotope 24, we don't know how much of it, but we'll call it X. And isotope 26, and we've got 10%, sorry, we've got 100 minus 10, which is 90, minus X, which was X used earlier, and we can expand that over 100. So that's what your statement should look like. We can expand it a bit by getting rid of the hundreds, make it a little bit neater. So if we times everything by 100, we get to 2,430 equals 24x plus 25 times 10, which is 250, plus 26 times 90 equal 2. Use a calculator on this one. 2340 minus 26x. And then we can resolve that. So we tidy things up. So we got minus 2x. Oops, sorry, I just jumped there. It's just my hand brushing against the thing on the side there. So we've got minus 2x. Oh, well, move it over to the side. So 2x equals 2590 minus 2430, which equals 160. So therefore x equals 80. So if x equals 80, 90 minus x must equal 10. So that's the percentage of magnesium 26. Not hugely difficult, but once you've seen it a couple of times, you can sort of work out what you need to do. Right, so question here, the time of flight. So we're looking at half mv squared is the kinetic energy. We want the velocity. The velocity equals, we need to rearrange equation, 2 times the kinetic energy over the mass, but the mass has to be in kilograms. Okay, and that's the square root of that. So it's the changing of the units. So what we need to do is we need to work out the mass, and we've got isotope 25 grams. So let's divide that by 1,000 to get kilograms, and times it by Avogadro's number. So which is, sorry, divided by Avogadro's number. Which is per mole. So where's the calculator? So that's 4.15 times 10 to the minus 26 kilograms. So we can put that into the equation. That gives us the equation should look like this when we put the numbers in. So, but 2 times the kinetic energy, which is 4.52 times 10 to the minus 6, times that by 2, that's we've done that, divided by the mass that we've just calculated of an individual particle. And that should give us the velocity in meters per second. Bash that out on the calculator. Right, and we've also got velocity equals distance times time. So distance equals velocity times time. And the time they give you in seconds there. So it's a matter of using that 147,565 and timesing it by the time, which is 1.44 times 10 to the minus 5 seconds. Equals, it needs to be a sensible answer because it's not going to be thousands of meters, is it? So you can have a real think about what sort of distance is. Distance here is 2.2 meters, 2.3 meters. That's a reasonable value. It's going to fit in the laboratory, isn't it? So, right, next question, balancing equations. So to balance this equation, now balancing equations used to be quite easy, but it's tricky at this level. It's all about technique. If you've got time to get it done within a minute or so, great. If not, come back to it later. This is really about exam technique. Okay, the second one is much more straightforward. That's a terrible, that first one is really difficult. Suggest reasons why sulfur dioxide, the byproduct of this process, is removed from the exhaust gas. Well, it's primarily because it causes acid rain. And all the problems that's produced, and it's also toxic. I don't know why that line's there. Okay, a passenger jet contains 4050 kilograms of copper wiring. Okay, so we need to find out the moles of copper. So 4050 times 10 to the 3 divided by 63.5. Doesn't matter if you use 64, but 63.5 is what they give it to you. And that should give you a number of moles of (63775 moles). Now that's the moles of copper. The mole ratio of copper to the copper rock ore is a 1:1, so that gives you the number of moles of the ore. That number just goes in moles of the copper ore, but it is only 1.25%. So we're going to have to factor that in. We can easily convert the moles of copper into the moles of copper ore into the mass of copper ore just by adding up and using the relative masses. So if we quickly work it out, we find that the relative mass of the copper ore is 183.5. So if we times the moles by 183.5, we can get the mass of copper ore required. Not sure what's taking so long here. Oops. Keeps jumping about here. So that gives us a mass of 117. Needs to be more than that. 0.3 times 10 to the 3 grams. We then need to take into account that it is it's only 1.25%, so we need to scale it up. We need to divide by 1.25 and times by 100. And that should give us a much bigger mass. Nine three six 0.00000 grams, but that needs to be converted into tons, so we divide by 1,000,000. Okay, next one. Copper can be produced by the reaction of carbon with copper 2 oxide. Here's the equation. Calculate the percentage atom economy. So we need to work out that copper is 63.5 and carbon dioxide is 12 plus 16 plus 16, which is 42. So if we take there's 2 lots of copper, so 2 lots of copper, that's the desired product. All the products together are the copper and the carbon dioxide. And we need to times it by 100. It's missing. $127 divided by 171. Yeah, there you go. Times by 100, times by 100. That should give us your percentage atom economy. So how much of the copper is in all of the products. So that's what we're looking at there. I'm still waiting for an answer. And the answer is 74.269. It does say look at the answer to appropriate significant figures. And if we're looking at them, it looks like it's only 3 significant figures. So it should be 74.3. Important to look at the significant figures. Right, question 3. Meaning of the term electrophile, power of an atom to draw or to attract a pair of electrons in a covalent bond. Got to have in a covalent bond. It's not just pulling any old pairs of electrons. Okay, because the difference in electronegativity causes the dipole you've got to have that concept of it's a pair of electrons attracting a pair of electrons in a covalent bond. So how does a permanent dipole force arise between hydrogen chloride, where you've got a difference in electronegativities? Therefore, you get dipoles, and then you've got opposite dipoles attracting each other. So a lot of people get the first mark, oh yeah, we talk about dipoles, but then they forget to explain how do the forces arise. Well, he's got the opposite dipoles attracting each other. And the attraction obviously is electrostatic. Right, next one. So what do we need to do for this one? We need to work out the number of pairs of electrons and work out the shape. So the first one is silicon tetrahydride, so that's going to have 4 pairs of electrons. 4 pairs of electrons would indicate that it's going to be tetrahedral. Now it's symmetrical, and the pull of electrons is, so therefore there is not going to be a permanent dipole across the whole of the molecule. The next one is pH3. So how many pairs of electrons? We've got 4 pairs of electrons, 3 bonding, 1 non-bonding. So therefore it should be trigonal pyramidal. Some Marx schemes will accept tetrahedral based on a tetrahedral, but I would learn the thing. Now, beryllium chloride is 2 pairs of electrons, and that's it. And they're both bonding, so therefore it's going to be linear. And it's symmetrical, so there's no dipole, there's no permanent dipole across the molecule. And the last one is 4 pairs of electrons, but chlorine is much more electronegative. So there's going to be a dipole across that molecule. There are 4 bonding pairs, but because chlorine is much more electronegative, it'll pull the electrons towards it. So that end will be that's very electronegative. So therefore we can draw in the dipole. So it's going to be based around a tetrahedral, but it's going to be a polar molecule. So we can tick pH3, because that's got a dipole across it. And we can tick tetrahedral. Marks would be 1 for each row getting it correct. So tetrahedral not ticked, trigonal pyramidal ticked, linear not ticked, and tetrahedral ticked. Right, next question. What are we doing here? We're looking at which one is the smaller ion. Magnesium 2+ is the smaller ion, so you have to put the 2+, because you can't just put magnesium, it is the 2+ ion. Why? It's got more protons than sodium 2+. But they both have the same number of electrons. You need those 2, so 1 for the identifying it and 1 for the 2 points together. Okay, write an equation to show the process first ionization energy. Most people get this one. A lot of people forget that the state really matters. So it's okay having the equation, but without the symbols of state for gas and gas, it wouldn't work. So that's really important. Okay, next one, we're looking at first ionization energies across the period. And it's period 3. The thing we need to look at is the fact that there are certain dips that occur. Okay, so you need a small dip in that one, and then it goes up, and then you need a small dip in the next one. And that's roughly the sort of range you need to be looking at. Okay. Then we need to explain why the first ionization energy of sulfur is different from that of phosphorus. Well, it's all to do with the fact that sulfur has got an orbital with a pair of electrons in it. So it's worth putting down the electron arrangements. Here you are. So the third p orbital, whereas phosphorus has got 3 unpaired electrons, and what you've got is repulsion between those electrons in the 3p. So paired electrons in 3p repel. Well, because they're both negative, that's why. So marks, 1 mark for repulsion, paired electrons. Right, question 5. This question is about the chemistry of group 2 elements. Write an equation for the reaction of calcium with water. Calcium reacts reasonably quickly with water to form calcium hydroxide. Remember, metal plus water produces hydroxide plus hydrogen. The pH is not as high as it should be because calcium hydroxide is not that soluble. So though it's got a lot of hydroxide ions, rather, because it's not very soluble, it doesn't release as many. What is the trend in solubility in the water? Well, it decreases. Of the barium, remember, is very insoluble. Now, this question was written incorrectly. Sorry about that. It was an old version of the test, and it shouldn't have been there. It should have been, what's the reagent to test for sulfur dioxide, and it's barium chloride, which is acidified with hydrochloric acid. And the equation for the reaction is Ba2 plus SO4 2 minus. Goes to BaSO4, and it's a solid. Now, everybody would have received a mark from that in the 2020 paper, even if you probably worked it out, because it's not really fair. But it was just an error that crept in because we couldn't get it's just an error that crept in. Explain why the melting point of calcium sulfate is high, because it's about ionic bonds, isn't it? The strength of the ionic bond. Strong attraction between oppositely charged ions requires a lot of energy. So you'd probably, that'll do for this one, but normally a lot of energy is required to break them. But it's really just about an ionic bond. Right, iodine, so they want you to give the abbreviated what do they call it? Electron configuration. Oh, look, there's not much space here. Okay. We'll do a lot more of these questions in the future, but there's a particular technique of answering them. What they're doing is they're comparing the melting points of iodine and hydrogen iodide. Okay, you need to state that both are simple molecular. One has permanent dipoles and one has van der Waals forces. So you need to put the intermolecular forces. They're quite weak, so for both of them are quite weak, so the melting points aren't very high. It's important to say it's not the covalent bonds that are breaking. Iodine, I know it's van der Waals forces, but by using the data, you can see that the iodine must have stronger intermolecular forces. Their van der Waals forces are stronger than the permanent forces in the hydrogen iodide. It's easy to assume that it's always going to be permanent dipoles is stronger. It usually is the case, but if you've got enough electrons with a big enough dipole, you can have the melting point higher in a van der Waals force. And this is an instance here, and it's trying to catch you out. Now, I've squeezed it in the side here. You could have used the back of a piece of paper or something like that and just written it on there. Clearly, it needs more space. I think in later versions of this exam, you are given more space. Now, there's a lot more detail that has on how to mark this one. Essentially, if you get all those points, you get 6 marks. If you get most of those points, you get 5, then 4, then 3, then 2, then 1. We need to practice these in a lot more detail, and that's something that happens at the end of tends to happen at the end of the course. So getting back to the mark scheme, stronger van der Waals forces using the data provided, so you need more energy to break, and then even though there's a permanent dipole, it's weaker than the intermolecular forces in iodine. Why does iodine not conduct? Well, we tend to put no free electrons. You need to change that so it's no delocalized electrons. And that's a sort of change you need to make from your knowledge and explanation from GCSE. Right, deduce the equation for the formation of hydrogen iodide from its elements. Well, hydrogen iodide is made from hydrogen and iodine. You can have the multiple of hydrogen iodide, or you could have halves. So you could have done half H2, half I2, goes to one lot of HI. Like that. Okay. So next one, the triiodide ion is formed when iodine molecules bond into iodine. What's the formula of ammonium triiodide? So you should know ammonium is NH4. And the nomenclature, it says triiodide, so that means 3 iodines. So it was really just ticking the last box there. Right. Right, so here we're looking at include the pairs of electrons that influence each shape. So IF3, what we're looking at here is there's iodine has got 7 electrons in its outer shell. It's got 2 lone pairs here, and the 3 are used in bonding, so it can expand its octet. The best way of doing that one is by having a trigonal planar. So if we looked at the electron shells, iodine has 7 electrons. It expands its octet to share some with fluorine. So it's going to have more electrons in its outer shell than just the 8. But it does result in 1, 2, 3, 4, 5 pairs of electrons, 3 bonding, 2 non-bonding. And that gives us a trigonal planar shape. Right, if we look at the other one, we've got IF4. So it's also a minus ion, so it's gained an electron. So therefore, the reason why it's done that is because what it's trying to do there is it's pairing up its electrons. So the IF4 minus 1 ion. So if we work out the pairs of electrons here, we've got 1, 2, 3, 4 pairs of electrons that are bonding, and we've got 4 pairs of bonding electrons and 2 pairs of non-bonding electrons. So therefore that would probably have a square planar orientation. That should be in a bracket with a -1. Okay, deduce the oxidation state of iodine in the following species. So iodine is a -1, it's a +5, and it's a +7. Okay, next question. Write an expression for the Kc of this reaction. Kc is, remember, it's products over reactants. So we're just going to use Y because it makes life simple. Y, concentration of Y times by H2O, concentration squared, because the stoichiometric number is 2. And the same with X, concentration of X, times by methanol, and concentration of methanol, which is reactant, methanol, and that's squared because of its stoichiometric value. Right, so they give us a mixture of X and ethanol. So what we need to do is write out the equation. We need to put down the ratio. I can't use X here because that's going to get confusing. Let's change that. I think we just call it A. So the ratio is A to 2A to A to 2A. Then you put your initial amounts in, and the initial amounts was 0.32 and 0.84 and 0 and 0. Then you put your you write your expressions. So 0 plus A gives you 0.26. That tells you that A is 0.26. So 0 plus 2A, 0.32 minus A, 0.84 minus 2A. We know what A is because looking at that expression for Y, A equals 0.26. So we just put those numbers in. So that's 0.52 for the water, 0.06, and therefore the last one is 0.32, and we can put those values in. Those are mole quantities. That's what it's looking for. Now, if we look at the expression, it's not going to have units because it's symmetrical in terms of the quantities above and below. So all the units of volume and moles will cancel, so there are no units. And to work out Kc, we just put the values in, the equilibrium quantities, in the expression. Making sure you've got the right order. This is where people make mistakes. They put the wrong values in the wrong places. So 0.52 squared times by 26 over 0.06 times by 0.32 squared. Bash that in. We should get 11.44. Are they asking for, whatchamacallit, significant figures or the right number of things? I don't think they are. Okay. It says predict the effect of a lower temperature. If you see the reaction is exothermic, so a lower temperature will push the equilibrium to the right, so you're going to get more product than reactant. Oh, I've just jumped again. More product than reactant, so therefore it's going to get bigger on the top. The expression is going to get bigger on the top and lower on the bottom, so therefore it's going to increase. Right, next question. Sodium bromide reacts with concentrated sulfuric acid. Tricky equation, okay, because it's you get two sorts of reactions. You get an acid base, and you get the redox reaction. Whereas sodium chloride, you only get the acid-base reaction. Explanation, well, it's to do with the fact that the bromide ion is bigger. So therefore, it has a greater distance between the nucleus and the outer electrons, and it's got more shielding. So therefore, the outer electrons are more easily lost or more easily removed. Should be more easy to lose outer electrons. Just writing this. The outer electrons should be more easily lost, but you know what I'm trying to say. Why? Because it's bigger radius and more shielding in the larger bromide ion. Right, there's another classic question down here. Just work out where the marks are. One for the equation, one for the bigger ion, one for the explanation. more easy to lose outer electrons. Okay. A colourless solution contains a mixture of sodium chloride and sodium bromide. Using aqueous silver nitrate and other reagents of your choice, develop a procedure to prepare a pure sample of silver bromide from this mixture. Explain each step along the process of the procedure and illustrate your explanation with equations. So the key thing here to do is you can make a precipitates using acidified silver nitrate, using nitric acid. And then with the equation you're going to get Ag plus Cl minus goes to AgCl solid. And the next one is going to be Ag plus Br minus goes to AgBr solid, and that's going to be cream. Now we need to remember that one of these is soluble in dilute ammonia, while one of them is soluble only in concentrated ammonia. Oh no, that's shouldn't be concentrated ammonia. Sorry, that should be dilute ammonia. If we added concentrated ammonia, it'll dissolve both of them. So let's just go back a bit. So add dilute ammonia. And what that'll do, that will dissolve the silver chloride. So you'll be left with a precipitate of silver bromide. So the equation for that one is going to be 2 lots of ammonia plus AgCl solid goes to Ag NH3 plus Cl minus. 2 lots. That should be ammonia. Sorry, I've just seen that. That's I've got NH2. That should be NH3. There's an error on my part. Okay, and then you can filter off your silver bromide. You can collect the residue and give it a wash and leave it to dry. So all of that will give you 6. Write an ionic equation between chlorine and dilute sodium hydroxide. It's an ionic equation, so normally you would have done this one as NaOH, but because it's ionic, we're just looking at the important ion, which is hydroxide, and then you would normally put sodium chlorate and sodium chloride. Now the chlorate is +1 and the chloride is -1, so that's the second mark. Obscure part of the specification, lots of people forget to learn it, but it appears quite often. Right, Maxwell-Boltzmann distribution curve. Here we are on the appropriate diagram. Mark the value of most probable. Okay, when it's cooler, you get a shifting of the peak, so the peak is to the left and it's higher, and it drops below the peak, sorry, below the line, so, and it stays below. So they sometimes say it crosses the line once. With reference to Maxwell-Boltzmann, just explain why a decrease in temperature decreases the rate of decomposition of this gas. What we're looking for is fewer molecules with an energy greater than the activation energy. Which is EA. So we're looking at that's 1 mark. Fewer successful collisions or successful reactions, but it's more than that, because it's not just fewer, it should be about the frequency, so the fewer collisions per unit time. So it's not just about fewer collisions or less collisions, it's about the frequency of the collisions being less, the frequency of successful collisions being less. I think that's it.